Okay, so we are going to have the first example for the tutorial, which is going to be about the force fit. We have a bronze bushing to be installed in a steel sleeve once again, as shown in the same diagram of the bushing that have the inside diameter of 50 millimeters and a nominal outside diameter of 65 millimeters, which has a tolerance limits of zero point 0.1 positive and zero point zero 0.05 positive. So that's mean that the outside diameter of the pushing is going to be 65, wait a second. Tolerance limits are given as zero point 0.1 and 0.05. The steel sleeve has a nominal inside diameter of 65 millimeters and the outside diameter of 90 millimeters. Yep. So now that's the mating surface, 65 and 65. So the tolerance limit is going to be 65.1 and 65.05. Okay, these are the two limits we have there. Now for the sleeve we said that have a nominal inside diameter of 65 and the outside diameter is 90 millimeters, which has a tolerance limit of 0.025 and 0. That means that the maximum diameter we can have for the hole is going to be 65.025 and the minimum diameter is going to be just 65. Now the E value for the steel is 200 gigapascal and for the bronze is 120 gigapascal. And we're going to use the portion ratio to be equal to 0.3 for both materials. So we need to do the same process of first determine the limits of the interference that will result. That's mean the delta. And then according to the maximum interference from A, compute the pressure that will be developed between the pushing and the sleeve and the stress in the pushing and the sleeve and the deformation in the pushing and the sleeve. So we are going to repeat the same steps that we've done earlier. First, we don't have to use the tables, and this is something very good, at least if you don't like to use them. So once again, we're going to determine the amount of the interference from the design of the parts, applying these limits to the basic size will give you dimensions, limits of the internal diameter of the hole and the steel sleeve and the outside diameter of the bronze insert respectively. So for the steel sleeve, we're going to have, as we mentioned earlier, the 65 plus 0.025 for the maximum and 65 minus 0 for the minimum. For the bronze pushing, we're going to have 65 plus zero point 0.1 for the maximum and 65 plus 0.05 millimeter for the minimum. So the limits interference will be 0.025 and zero point 0.1. So what we've done is, once again, we're going to do the following. For the shaft, the maximum is 60.05 minus the maximum for the hole, which is 60.025, and we're going to have the 0.025. Now we're going to have the maximum diameter for the shaft minus the minimum diameter for the hole, and this will give me the zero point 0.1 millimeters. Now, of course, the C value, the B value, and the A value are going to be all the diameter we have divided by 2. So we can put that in the equation of the pressure using all the parameters that we've been gained from the question. And we will get the answer to be equal to 64.926 megapascal. I would like you actually to calculate that yourself and double check this answer. Now compute the tensile stress in the step number 3 in both the outer member and the compressive stress in the inner member using the following equation respectively. So these are the two equations we have. We're going to put the parameter in the first one, and we will come out with the answer to be equal to 206.51 megapascal. We'll repeat the steps for the sigma I, or the compression stress we have on the shaft, and this will give me the answer to be equal to negative 253.1 megapascal. Now, step number 4, the increase in the diameter of the outer member due to the tensile stress and the decrease in the diameter of the inner member due to the compressive stress can be computed with the following equations. So again, we know the C, we know the B, we know the VO, and we already calculated the pressure, and then we can apply the equation for the first one, and we will get the answer to be equal to 0.0743 millimeters. For the second one, we're going to get the answer to be equal to negative 0.1266 millimeters. That's it for this example. We just simply calculated the same parameters that we had earlier using the same equation, and we got the answer for this design.